It's time to move to the second topic of this morning, future of energy. Are there any other nuclear solutions? And our guest is Bernard Bigot, General Manager of International Thermonuclear Experimental Reactor.
It's my pleasure to participate to this Planetiers World Gathering. And so I am very pleased to introduce the ITER project, which tried to open the way to a new energy future. As you see, the work site is quite explicit. It's a very large project, quite ambitious, in order to demonstrate the feasibility of hydrogen fusion. Fusion is quite common in the universe. Indeed, it's fusion which powers the sun and the star. And as maybe you know, it's just because you have two light atomic nuclei as hydrogen, getting very close together, okay, and overcoming the large repulsion, electrostatic repulsion at long range, and coming so close that they will fuse together with under the effect of the short range nuclear attraction. So is what we want to reproduce on Earth. We could not do exactly as it is in the stars and the sun, where it is the gravitational forces which make the hydrogen to fuse. We will make it indeed under the very high capacity of electromagnetic forces, magnets, to accelerate the hydrogen nuclei, make them colliding and very high speed with a temperature which is of the range of 150 million degrees. And when they collide, they will produce the helium and the neutrons. The helium will get away from the collision with a 5 times larger energy content, and the neutron, okay, 20 times, as you see on this picture. And these two particles indeed will collide with the wall and transfer their kinetic energy as to heat. So the key element we have to assemble is indeed the large magnetic cages. As you see on this picture, the cage is as large as 20 meters high and 20 meters large. As you see, compared to the size of the man, which is at the bottom of the slide. And you have to assemble these coils, which are constituting the magnetic cages, 18 vertical ones, 6 horizontal ones, plus the central, what we call solenoid, magnetic soil. You have to assemble them with a precision of millimeter. Why? Is because the particles are running, circulating with very high speed, and if the shape of the circle is not perfect compared to the shape of the vacuum vessel, they will collide with the wall before they could fuse. So the challenge for ITER is to comply with the expectation of very high precision and large size of the component. While all the ITER partners, ITER members, want to contribute to this discovery of hydrogen fusion capability, is because fusion has many advantages. It could be a massive, predictable baseload power complementary to renewable, because we could switch on and switch off when you have, for example, clouds or night. It's safe, intrinsically safe, because you have only very little quantity of material fusing at a given time, 2 grams in this very large vacuum vessel chamber of several thousands of cubic meter. And if any parameter go wrong, immediately the plasma will fade off, will stop, and there is no energy remaining which could make some fusion of the core as it's happened in fission technologies. We will produce only helium, so no impact on the environment, no impact neither on the climate, because no greenhouse gas emission. And it's virtually unlimited fuel for hundreds of millions of years, because they are globally distributed. It's water and lithium in very small quantity. And last but not the least, we produce very small quantity of radioactive material which will not last for very, very long. The challenge is so large indeed that we need a very large cooperation. We are very pleased to know that we have been able to gather together 7 large partners representing more than 35 different countries. All of them feel seriously that ITER could be the way to demonstrate hydrogen fusion capability. And for that, they have accepted to provide the various components, what we call in-kind contribution, in order to be sure that their best company could demonstrate their capability to manufacture this very complex and challenging component. It's what has been decided within the ITER agreement, signed indeed in 2006. And as you see, there is 6 non-European countries, each of them accepting to contribute for a value of 9% of their in-kind contribution, and Europe, because ITER is built in Europe, has accepted a share 5 times larger. So, where are we now? We are progressing, and I am pleased to say that now the project is over 70% complete when we go from early design through first plasma. And we have largely been able to maintain critical activities during the COVID-19 pandemic to preserve the overall project schedule. It's also a large achievement with the support of all the ITER members. We are going on with a very strict schedule. On this slide, you see that most of the large components will arrive on site in 2020, 2021, 2022 to be assembled before we have the first plasma by 2025. Very challenging schedule. It could seem long, but indeed the complexity of the assembling and installation is very, very high. And after the first plasma, we will have what we call a stage approach to the full fusion power with 2 brands of hydrogen, deuterium and tritium, by 2035. This project is very challenging. Very large coordination was needed. And so I am pleased to see that with this strong management, we have been able during the last 6 years to move from nearly a greenfield working site to a very, very dense working site, as you see on the picture in June 2020. We are now more than 75% of the installation civil works completed. As I mentioned, 2020, 2021 will be really decisive years. So far, we are pleased to see that in 2020, we have experienced the deliveries of the first Poloidal Field Coils from Europe and China, the first sector vacuum vessel from Korea, and many, many other components was on their way to the ITER site, coming from all over the world. And now, after we finalize the construction of the main civil works, we are ready to install equipment. There is, for example, the cryostat, base and lower cylinder, the first Toroidal field coil, vacuum vessel are on site and ready for being assembled. Just a few illustrations of the real progress. Recently, we experienced for construction. On this slide, you see a drone overview of the site with the central piece being the Tokamak Complex building, where we will have this Tokamak able to fuse the hydrogen with the very high temperature I mentioned. And behind you have the assembling hall. In order to prepare the assembling of the various components, you have to put in the Tokamak building by the roof, because it's so large you could not put them through the door or the windows. And also some very large equipment, as you see, as a cryo plant, the magnet power conversion building, the huge switchyard, and the heat rejection system. I will speak in a few minutes. Very recent progress has been experienced. Indeed, as you see, the Tokamak Complex has been delivered by March 2020. The first crane access from assembly hall to Tokamak building has been opened by the end of March also. A crucial milestone indeed has been achieved. Very proud of this successful installation of what we call the 1,250 tons base of the cryostat, which has been procured by India, which was successfully inserted in the Tokamak pit. As you see, now the big crane has lifted off over 50 meters above the ground and moved in the what we call bioshield wall, a huge cylinder, 30 meter high, 30 meter diameter, made of concrete. And so it has been very well positioned with a precision which is with a tolerance under 3 millimeter at all metrology point. For successful success for the base, but also success for the lower cylinder, by the end of August, we have been able to move this cylinder. It's like when you make a can with the base, the bottom, and the successive cylinder. The cylinder has been installed successfully, and now it fits the two pieces, 30 diameter each of them, and we will weld them. Indeed, we start the welding even today. So, when we pass this milestone, starting the machine assembly, we thought it was worth to invite all the ITER members at the higher level of their authority to notice this achievement and also to express their views about the ITER project. And we are very pleased to say that they were very positive and encouraging us to go on accordingly to our schedule. We are now ready for first pre-assembly. As you see on the slide, the first vacuum sectors, nearly 20 meter high, okay, 450 tons, very high precision, has been delivered and is now tested. We test that they are leak-proof. Not only the Tokamak is progressing, but also the plant. Here you see the cryogenic plant, which is with a lot of material, and very soon we will start the commissioning. The electrical network also, we are now connected to the French grid, and yesterday, very precisely, all the 7 large transformers has been fully connected to the French grid and operating. We need to transfer the power, and is why electrical components coming from China, India, Korea, and Russia are installed. Here you see what we call the bus bar, these huge aluminum bars which will be able to transfer the electricity. They are not superconducting material, but they are very high level of technologies. And last but not the least, since we will produce a lot of heat, we need to cool down the steam, to cool down the hot water, because we flew back to the river. On site, we are now manufacturing some of the components which could not be transported. For example, the large horizontal coils, which could be up to 24 meters large. And so we are on our way to complete. Some other components are coming from all over the world. For example, the coils, the vertical coils, arriving from Italy and from Japan, this spring. The very large coils also, but only 10 meters large, arrive from China, requested on the European deliveries, and you see it has been very successful. We also received the vacuum vessel sector number 6 from Korea. Very impressive process for having the delivery fully safe. Some also big progress. This week precisely we received from India the last part of the cryostat, which is what we call the top lid. All the pieces arrive early this morning indeed on site. Many other components are on their way to be delivered. As you see, for example, the magnetic feeder, the cable which will feed the coils, superconducting material, in order to be able to feed up to 70,000 amperes. And you see some other components from Europe and Japan or India. Korea, Russia, US, all of them are on their way to complete the manufacturing of the component and to deliver them to the site. So I hope I convince you that ITER is on its way to be successful for first plasma by 2025, full fusion power by 2035. We are really committed, and we expect that we will offer a new opportunity for the world to rely on a safe, clean, massive way to produce energy for the best of the humankind. Thank you very much for your attention.
A big applause for Bernard Bigot, and now live from France, Laban Coblentz is the head of communications, ITER. Thank you so much for coming, Laban. Good morning there in France. And we are used to look at the nuclear energy as a clean source of energy, but also as a dangerous one. Should we think it over? Should we rethink this question?
Well, thank you very much, Mr. Pinto, and thank you to the Planetiers, and congratulations on really what you are doing with this gathering. I would just say I found it very interesting, the contrast between the two first mini sessions, in which one was very focused on behaviors, and then what you just saw very focused on technology. And personally, I think it's going to take both. To respond to your question about nuclear, all of the nuclear plants in the world, the 400 or so plants, are nuclear fission. They involve a couple of 100 kilos of uranium, a chain reaction that, if uncontrolled, can be out of control, cause a Chernobyl, a Fukushima, etc. What we're working on here at ITER is also following Einstein's equation, E = mc squared, but it is inherently safe. No chain reaction, 2 to 3 grams of hydrogen at any point. And so there is no possibility of a meltdown. Mm-hmm. There's no production of long-term nuclear waste. It's simply technologically very, very, very challenging.
So we were talking about cheap, very cheap, and very safe energy. And
yes.
When can we have that?
Well,
when can we get there?
Yeah, I'll answer the question, but the answer really depends on the degree to which we want it. There's a very famous Russian scientist who said, we will have this when the people of the world believe they need it. I would say that at the rate of government investment currently, it depends a little bit on where you look. So ITER itself will be demonstrating by the late 2030s the feasibility of this at a grand scale. If you look at what comes after, China is probably, among the 7 ITER members, China is the most driven, the most motivated to produce as soon as possible. So they project bringing energy to the grid even in the 2040s. If you look at Europe, if you look at some others, those things are closer to mid-century or even a bit later.
But we are facing in Europe a trend that Europe is leaving the nuclear behind. Do you still believe that we can turn it around?
Yeah, I do. Again, because this nuclear is not the nuclear that we are familiar with. And so, frankly, when we talk to the strongest Green Party advocates of renewables and so forth, we have seen quite a welcoming of the hydrogen fusion technology. And from our standpoint, this is something that needs to be complementary. While we are strongly supportive of wind and solar, which, to be honest, are really fusion, because the sun is producing these technologies, it's just fusion at a distance. And when we envision a future of clean energy, we hope that wind and solar will be capable of sustaining clean lifestyles for the distributed energy needs, but for powering mega cities where most of the population lives, for powering industry. If we are going to enjoy something close to the lifestyles that we have, even following Professor Monosing's recommendation of less greed and more sustainomics and sustainable lifestyles, we will still need a strong baseload power, and we think that will be fusion.
Safe, clean, and very cheap energy. We'll be looking for that as soon as possible. Laban Coblentz, thank you so much for your presence here at the Planetiers World Gathering. A big applause for Laban. Have a nice day.